Okay, so let's start our very interesting topic of electronic configuration. Now, what is an electronic configuration? This is a concept that will tell you how the electrons are arranged inside an atom, right? So we know that an atom is made up of the nucleus, and the nucleus is surrounded by electrons. Now, in electronic configuration, we'll try and understand how these electrons are distributed in the atom. Now, let's start off with an appetizer which will tell us the old concept, which is the easier concept for some people, to arrange the number of electrons in an atom. Now, before moving on to the arrangement, let's remind us how do we calculate the number of electrons in an atom. In a neutral atom, the number of electrons is just equal to the number of the protons, which is the atomic number of the atom, right? So, for example, if you have hydrogen, the atomic number is 1, therefore the number of protons is 1, and since this is neutral, the number of electrons will be equal to the number of protons, which also becomes 1. The same goes for any, like for neon, the number of protons is 10, and therefore the number of electrons is also 10. Now, our job is to arrange those 10 electrons in the atom, okay? So let's get started on this. The very first concept that we study in here is how do we arrange electrons in a shell by the Bohr-Bury's principle. Bohr-Bury's principle starts off like this, that whenever you have an atom, you have a nucleus, and then there are shells around the nucleus, just like the planetary system. Like you have the sun in the middle, and then you have orbits. So we'll just name the orbits. It starts with a K shell, the L shell, and the M shell followed by that, and that's how it goes on. Now, we have the nucleus and we have the shells. Now, the shells have electrons in them. There'll be electrons that will be moving around the nucleus. Now, how do we calculate the number of electrons that can be housed in these shells? Those different shells will be able to house different number of electrons. That is given by 2n squared, n being the nth number of the shell. For example, K is the first shell, and therefore the n for the K shell is 1, the n for the L shell is 2, the n for the M shell is 3. Okay, so that's what we have written here, K, L, and M. The n for K is 1, 2, and 3, right? Now, how do we calculate the maximum number of electrons in the K shell? We use the formula 2n squared, okay? So, we calculate 2n squared. For n is equal to 1, 2n squared becomes 2. For n is equal to 2, 2n squared becomes 8. 2 times n squared becomes 4, and 4 times 2 becomes 8, right? Similarly for n being 3, n squared becomes 9, 9 times 2 is 18. So this 2n squared will give you the maximum number of electrons that are possible for these different shells. Now, when we have this, let's try and start to do some electronic configuration. Are you ready? Okay. For hydrogen, which is 1, the number of electrons is 1, so the K shell can hold maximum of 2, so this one easily accommodates 1 electron, right? So K takes 1 electron. Now, if we move for helium, the atomic number is 2, therefore the number of electrons in helium atom is also 2. K shell has the maximum capacity to house 2 electrons, and it takes 2 electrons in here. Now, when we move to the lithium, which is now 3, now the things become interesting. The first 2 electrons are being housed in the K shell, but this is not enough. We have a third electron that needs to be housed. So where will it go? The K shell is full. Now, since the K shell is full and we have one more to go, we move on to the next orbit, which is the L, and we house one electron in the L, right? And this is the way we move forward, okay? Similarly, let's take an example of nitrogen. So nitrogen, the number of electrons is 7, so 2 goes in the K shell, the remaining 5 go in the L shell. Pretty simple, right? Okay. Now, this story goes on. Now, till neon, we have 2 and 8, okay? No problem, because neon, the atomic number is 10, 10 electrons, 2 goes in here, 8 in there. Moving on to sodium, which has 11 electrons, 2 goes in here, 8 in here. Now we have one more to go. What do? We move on to the next shell, which is the M shell, and 1 goes in here. Pretty simple, right? And we keep on doing the same thing. Now let's take an example of the potassium atom, which has 19 electrons, okay? Now, 2 goes in here, 8 goes in here, and 9 goes in here, right? 2 plus 10, 2 plus 8 gives 10, 9 remain, and M shell can have a maximum of 18 electrons, so we put in 9. This is wrong. Why? Why can't it take 9 electrons? Because the maximum number of electrons is 18, right? Why can't we put in 9 electrons in here? Because there is a third part of this Bohr-Bury's principle, which is the outermost shell, or the valence shell, cannot have more than 8 electrons. Why? We'll see that, why this happens. Why we can't have more than 8 electrons? Or does all atoms require to adhere to this rule or not? So this rule is called the Octet Rule. Why? Because the outermost shell cannot have more than 8 electrons. 8 comes from the word octet, so there is this rule, Octet Rule, okay? Now, okay, so if there is a rule that the outermost shell cannot have more than 8, so unfortunately, we put 8 in here and move the next one to the nth shell, right? So this goes to the next shell, which is the nth shell. So the electronic configuration of potassium becomes 2, 8, 8, and 1, and not 2, 8, and 9, because of the Octet Rule. Now, similar things go on for the rest. Okay, let me introduce you to another bonus rule that comes in for the Bohr-Bury's principle, which is the penultimate shell, penultimate being the second but last. So the outermost is called the valence. The next one just behind the outermost is called the penultimate shell. The penultimate shell cannot have more than 18 electrons. So there is another rule that is coming in. So the first rule being the 2n squared, second being the octet, in which the outermost shell cannot have more than 8, and the penultimate shell taking no more than 18 electrons. So when we have all these rules, for me things are getting already complicated, because if we take an example of something like a high atomic weight element like the lead, which has the atomic number of 82, we see that the electronic configuration is something like this, which looks really messy, right? 2, 8, 18, 32. The outermost is cannot have more than 8, and the penultimate cannot have more than 18, and that's why all this confusion is going on in here. So it becomes really complicated if you go to higher atomic weights. So what's the solution? The orbital configuration. Till now, we were looking into the orbit configuration, the shell configuration, in which you have the K orbit, L orbit, M orbit. Now let's move on to a concept in which we have orbital configuration, which simplifies this whole thing. So chemistry, which we will see, is all about simplifying, right? We don't want to get into complicated things like these. We want to we want to have a system which simplifies this electronic configuration. So the next simplified form of this orbital configuration, of this electronic configuration, is the orbital configuration. So let's move on to that.